We are familiar with different kind of energies such as kinetic energy, potential energy, light energy, thermal energy, electrical energy, etc. But beside this, a system containing some amount of matter, by virtue of its very existence, must possess some energy. So let us explain it with some example. For example, when a gram of ice at 0 degree centigrade melts, it releases 80 calories of heat energy. So where this energy has gone? Again, if this same amount of water, if now freezes into ice, then 80 calories of heat energy is again expelled. So from this it seems that the energy absorbed by the ice during melting remained within the water and it has been expelled when again it freezes back to ice. Take another of a Daniell cell. In Daniell cell, when zinc and copper sulfate react, then it produces electrical energy. Where from this electrical energy coming? Next, take the example of hydrogen and oxygen. If we put fire onto mixture of hydrogen and oxygen, then it explodes, producing mechanical energy. So where from this energy is coming? Next is the example of carbon monoxide and oxygen. If we put fire onto it, then it also produces heat energy. So we can say, unless the system had some inherent energy within itself, how could they, isolated from the surrounding, produces work or other form of energy themselves? So we can say, therefore it appears that a thermodynamic system containing some amount of or some quantity of matter, by virtue of its very existence, must possess a store of energy. This energy we call as internal energy or intrinsic energy. Every system has within itself a definite quantity of energy. This is called internal energy or intrinsic energy of the system. So the internal energy of a system depends on the state of the matter, that is the thermodynamic state of the matter, and hence on thermodynamic properties or thermodynamic parameters of the matter like temperature, pressure, volume, etc. The internal energy or intrinsic energy of a system is generally expressed by the symbol capital U or capital E. Next is the concept of system. To be able to apply laws of thermodynamics, we need to define a system. A system is any material or quantity of matter or enclosed energy enclosed by a boundary surface. The boundary surface may be real or imaginary, but the existence of the boundary surface is of utmost importance in order to define the system distinctly. For example, a quantity of a gas enclosed in a cylinder has real and definite boundary, but in case of a burning flame, we can choose the boundary as our choice, and this boundary is imaginary. Any other part or material or body outside the system chosen is spoken of as surrounding. A system and its surrounding constitute the universe. A thermodynamic system may contains one or more kind of matter, or may be homogeneous or heterogeneous in character. A system may be classified in various types depending on the types of boundaries. The boundary of a system is of mainly two types: imaginary boundary and real boundary. Again, real boundary can be again subdivided into two types. One is diathermal boundary, another is adiabatic boundary. A diathermal boundary is that through which energy exchange with the surrounding is possible, but mass exchange with the surrounding is not possible. A system enclosed by a diathermal boundary is called closed system. An adiabatic boundary is that through which neither exchange of energy nor exchange of matter is possible with the surrounding. A system surrounded by this kind of boundary is called isolated system. And in case of imaginary boundary, both exchange of mass and energy is possible through it. A system enclosed by a part or whole by this kind of boundary is called open system.